Hi everyone, today I wanted to do an Axisymmetric subsonic jet tutorial. This is using one of the many turbulence modeling resources provided by NASA. It's an experiment using a acoustic research nozzle jet, which is some NASA designed jet that has pretty nominal values. This is kind of the mesh they use. They actually provide grids that looks like this, so you can kind of imagine axisymmetrically that this is a some type of inlet and this is kind of all free stream. And so you see the jet expand. Where's the picture? Right here. So the jet starts actually. This is your x equals 0, and it expands outwards. And so I thought this would be a kind of cool tutorial because this goes into the realm of compressible flow. They talk about how it approaches Mach 0.5, and Mach 0.5 you do have compressibility effects. So this will be a CFD study on a compressible type of flow. And so getting started, the hardest part, the thing that I had to figure out first was where the heck do I find the design of this grid? If you try to download this grid is almost impossible to be used because it doesn't define the boundaries and it can only be imported into Fluent. You can use the grid if you use a third-party grid software, maybe like Gambit or HyperWorks or something like the HyperMesh, that would work. But for most Fluent users, the grid they provide is almost useless. So I had to look up these papers themselves. They don't even have, they show this. This is what they have. And it really doesn't show any engineering drawing. So I had to search up that ARN1 and ARN2, and I found this other paper called Validation of the Small Hot Jet Acoustic Rig for Jet Noise Research. Only in this paper, that was not mentioned anywhere in this resource, did I find an engineering drawing of the jets. Let me find them. No idea where they just went. Oh, here we go. So I believe this uses ARN2 with nozzle radius 1, and you can see this is pretty standardized. So I literally, and the thing is, the first thing you should know is this dang curve is expressed by some ugly equation. So if you actually want to do this correctly, you're going to have to make an equation from 0 to 6.825 to get this curve. And there's two straight lines attached to it. There's this curve, then this region of straight line, and there's this region of straight line. There's some other complexities, like a little bit of curving here, that I'm actually going to simplify for my CFD case, because I think this should be somewhat negligible, and I'll show you in a bit that it may or may not be. But what I did is, sorry, hopefully you didn't see that. But whoops, where is this? Oh, here we go. Sorry. So on XO, I simply did 0 from, it said to use 0 to 6.825. That's exactly what I did. I created points. I created 200 points to be exact, from 0 to 6.825. And I plugged in this equation. That's the equation it gives. And it gives me these values from a height of 3 to basically 1, which makes sense because the radius should be 1 so that the diameter should be 1. And then these points are created such that they can actually be put into Solidworks. And so I'm actually going to save this. Oh yeah, I saved it as a, you have to save it as a text file for SolidWorks. So in this tutorial, I'm actually going to make the design in SolidWorks, and then I'm going to export it to ANSYS Design Modeler and Mesher to make it. So I have a remote desktop that's from my university. So I am going to open a new SolidWorks. If you don't have anything in SolidWorks, that is unfortunate, and I really can't help you with that. I'm sorry. I am not aware of any way you can import a curve, or in Design Modeler you can import a curve, but you can't make that curve part of a sketch. So it's Design Modeler as a CAD outlet is pretty limited. So I think it's best to use something like SolidWorks. So in SolidWorks, what I do is I have that curve. Hopefully I'm not lagging too much. Lagging a little bit. Uh, hopefully that was it. Was that it? So this should be titled ARN2. Whoops. I'm gonna go to my, this is my text file, ARN2. So in SolidWorks, you want to insert a curve, get out of the sketch. Through XYZ points, browse, text files, and it will pop up. You can Google, if this is not working for you guys, just go on YouTube or some other videos that show exactly how to do this. It's really clear. Darn it, one thing I just made a mistake is I had this in millimeters. I need to change this to inches, so when you import it, the values are whatever the values are, or your, what do you call it, your current unit. So now when I re-import this, this will be under the inches. There we go. There we go, should be much bigger. So this curve is a separate entity and I want it part of a sketch. So I will click on this, convert the entity. So now I can try create what has appeared in here. And so the key features I'm going to incorporate is this curve, this straight line, these edges, and this straight line. So knowing, kind of trying to remember how it looks. I believe it looks something like this. A little bit of a straight line, bit of a straight line here, straight line here, straight line here, straight line here. This is the universal x equals 0, and this is the x equals 0 that's referenced in the papers. And so I'm not going to be able to use all of the same references, but I would try to use my best on what I think is most important. Starting with this straight line, this straight line is 0.25 and this one is 0.665. So I will reference this as 0.25. I will reference this as 0.665. I believe this total radius or total diameter is 8.5. So I will create a construction line such that I can dimension this. This should be 8.5. And I want this line and this line to be 30 degrees. And boom, I have a fully defined sketch. And this is basically all I need right now. And one of the things too, whenever you create a sketch in SolidWorks, you want to export it to ANSYS Design Modeler, it has to be a surface. So I have to insert surface, planar surface. I don't know where I read this. This is kind of something you have to do. So hopefully I'm either teaching it to you now or you now know this, ARN2. I just saved it as SolidWorks. I believe you can use SolidWorks to import it into Design Modeler, but I like using a step file. It's just one of the many types of ways that you can do it. So once I have this, I have ARN2 as a step file. I'm going to copy and paste this to my own computer. You guys might not be able to see. Okay, but I think I did it. So I'm going to open up my workbench. This is some of my old stuff that you guys may or may not have seen about. I had to do a couple test runs because it actually took me a while to get this working properly. So here we go. Now we're ready. We can open my design modeler. This might take a second. And so one thing I can talk about quickly is if you notice quickly about interestingly about this is they actually do this not as a 2D case. They do this as 3D, as a rotated system. So they started as 2D and they rotate it, I believe, 1 degree about the x-axis. And I ultimately do get something a little bit different than their CFD experiment, but I do this purely as a two-dimensional axisymmetric simulation. So if you do this 3D, it may or may not be more accurate, but I want to do this as 2D to keep it simple. And for those of you that may be doing an axisymmetric, different shape type of jet, but know that you may very well get different results if you do a 2D axisymmetric versus 3D axisymmetric, especially if you use a turbulent model. So once I open up my design modeler, I can import external geometry file. I have my 2D here. I will add frozen. One thing I see off already is my meter. I have my units in meters, but I believe when I import this, it maintains the old units and scaling as what I imported as. So that step file tells them exactly how big it is in inches. So that's why it's showing up as something like 0.1 meters. So I'm going to have this all in inches because that NASA report uses inches. So I know from this drawing that this part is 6.825, this is 0.250, and the x equals 0, the absolute x equals 0 is right here. So I can kind of draw that out, that this should be about 7, and it's about 7. What I'm going to do is I'm going to draw a domain that looks somewhat similar to what they provide. Something like this. So they kind of go backwards a little bit. They use the value y over r jet. R is 1 in this case, so kind of convenient. This y should just be 50 inches, and this is 80 inches wide, and it goes up to 60 inches. So that gives me kind of enough of what I need. On the xy plane, I'm going to make a new sketch. Okay, let me think about this really quickly. I have to kind of go back and forth. Yep. So I can start at the origin. And so this will eventually go 80. And so they go backwards a little bit. Let me think about this. So yes. So this starts at here actually. This is one way you can try to fix your mistakes. So it starts actually over there. It goes upwards to wherever this is at. And actually, I know where this height is. It's 3 because, oh wait, no, it's not 3. I'll have to look that up. But then, it goes up. It goes out, right? So I'm just going to draw it very, very loosely. I'm going to constrain this as vertical. So now because eventually I'm going to do a Boolean, right, of this. I want the fluid domain and not this actual thing. So how I'm going to do this is I need to make this fit exactly to this corner-ish. But I can do that because I know exactly the range and the spots of this. So in terms of x, I know that this, according to what I use, is 665.665 behind behind y equals 0, or I mean behind x equals 0. So I can dimension this horizontally as 0.665. Boom, and it should line up exactly. Oh, I do know this height. I know this height is defined by the total diameter is 8.5, so the radius is 4.25. So I can vertically dimension this. Boom, and I have it to that edge perfectly. I know this should be, if I am trying to mirror this grid, it's about 50. Y over R. R is 1, so it's 50 inches tall. I will use general. is way up here. Make this 60. And I believe this X is actually 80 from here. So it's 80 actually from here. I'm just going to somewhat arbitrarily make this here to here. So I know this is about 7. So I'll just make this 87 or so. 87. Yeah, so that looks somewhat like this domain. So now I'm ready to surface some sketch. So here we have it. I want to create a boolean, remember? Because I want to actually model the fluid outside. Hopefully this works. And voila. So I have one body. I should have... Okay, this is working exactly how I intended. And so now that I have my domain, it's important that I split it up into different regions such that meshing works well. And so if you guys remember, maybe in some of my videos I explained that meshing is very important to kind of imagine different sections as like rectangular regions such that you can make a nice face mesh. And so how you can see in this case, you can see that this is one region, this is one region, this is one region, and these are probably 3 different regions. I can tell you that this is actually 2 regions because they have this discontinuity. They have a sharp point here. This is probably one region, another region, another region, 1, 2, 3. So they probably have a total of 1, 2, 3, 4, 5, 6, 7. I played around and I think I actually had some issues with the pressure gradient due to this concentration. And I think I can actually simplify it and still get pretty good results. So to do that, I will want to make a new sketch because I'm going to project different lines on top of it. How I am going to have to do it is I am going to make simply 2 points. I'm going to have a point here on this exact edge and a point on this exact edge. You could draw the line first. I'm going to make the construction point first and then draw the lines to separate them. So this point I know vertically is the same. Oops. Oh, it's actually dimension to that other line. Whoops. So it's actually dimension height-wise because it was made to center that line. So I simply need to dimension it horizontally. How far is this from here? And to do this, I actually will have to look into... So, this is one of the lines I actually arbitrarily made up. So I'm actually going to have to go into my Solidworks. And this is where some of the hand waving comes in. So I'm actually going to literally measure. I'm going to use inches. Perfect. This point to this point. Yeah, this is a lot of hand waving. Copy. So, whoops. I'm going to dimension it actually to this point to this line. And I'm going to do it to exactly what I copied from SolidWorks. So this should be exactly to that point. And now corresponding to this point, I can calculate it by taking these lengths actually. So the distance is that 0.665, I'm breaking out a calculator on my phone right now, plus 6.825 plus 0.25. So that gives me 7.74. So I know my horizontal distance to here, 7.74. And this is actually quite important because if it's not exactly on that point, you're going to have edges that will not mesh properly. And for the height, I know what height this should be because it corresponds to my Excel points. So that line is parallel. That's a straight line from the bottom of this. So this bottom line Here, let me show just the points, just the values. It's actually this long number. I'm just going to copy and paste that into here. And this is the height. 99999 something. Boom. And I have my 2 points. Now I can draw my lines. The lines here, I'm going to go straight up. This line, I'm going to go straight up. This line, I'm not going to go straight across. I'm actually going to go somewhat, this is totally arbitrary too. So here I am jumping to a different version. This is something that actually I realized only once I tried it, that this value may actually be somewhat important. So I made this height to be about the height I see here. So I just drew this. I said this height corresponds to about this tick. This tick is 1/4, so about 4 or 5 y over r. So it's about 5 inches. So I simply paid V16 this dimension to be 5 inches, and that's how I got this line. To make it similar to this case, I made this line that's somewhat I made it, what did I make this? 18 inches, a little bit arbitrary, but it works. So this is kind of what I ended up eventually realizing works better, because when I first tried it arbitrarily for this line, it didn't work. So I actually already how to do this. So you guys are going to see kind of me walk through the final product. But once I make that, it's time to make the mesh. For supersonic flow, meshing is pretty important. It's not like a simple airfoil where there's kind of a lot of ways you can do it, and for airfoils, like you might be able to get the same results depending on different models and different meshes. So in this case, I had to play around this a lot. I meshed it all this direction. So remember, when you're meshing, you have to think about your regions in terms of quadrilaterals, because face meshing or a map mesh, you want to think of a region being divided this way and then divided this way. So I divided all this way, and I make this bias that you have to play around with, and I make it such that I want to focus in this region the most. I want this, or this because this is the supersonic region or the compressible region. So I'm gonna make this as refined as I can, and I want to make sure kind of around this region where the jet is going to be expanding, where there's still going to be compressible effects, that I will make sure it's refined. My second edge sizing, I choose it to be these 3 points, so it's going inwards this way. I have this 100 divisions across here, and I have it biased upwards. So I have it biased upwards to here, and once it's starting to expand, I have it kind of in this region. I have this here, so this goes this way, and then I have to divide it downwards. So this one, so the thing with this geometry is it divided this 3 ways. This is a curve, and these are those 2 straight lines. So I have one here, that's 200 divisions, and 2 that are 25. So on the bottom has to be 250, and it's biased a little bit towards one direction, towards here, because I want to focus on this region. Face meshing everywhere, edge sizing here upwards. I think it's good practice to make sure anytime you have an edge size, it's always in at least 2, maybe probably multiples of 2. I have it sized, I have it biased towards here. Because I'm focused in this region, I have this less divided, and then I have here 400 divisions. So this is where it's expanding, and you still may have compressible effects. So remember, Mach number around here, I'm expecting it to be about, where does it say? To be about 0.51. So that's not supersonic, but there's still compressibility effects. And so I want to make this as refined as possible. So I have 400 divisions, and it's all biased inwards. So biased inwards even up here. You mesh that, and you get something that looks pretty good, in my opinion. So it's refined here, refined the most in like this region. This is where you have expanding flow and a free stream coming in too. And it continues to expand. And one thing you see, I don't see any big shifts in volume. So that's one of generally you want one cell next to the next cell to not have a huge change in volume. The aspect ratio is a little bit big on some of these cells farther down the line, but the flow is in this direction. So generally, if the flow is in the direction of the cell kind of high aspect ratio, that's okay. So this is how it looks. Yep, looks good. Once again, like this aspect ratio is kind of high, but as long as the flow is this way, it's either perpendicular or parallel to that aspect ratio, you should be okay. Finally, before you export it, make sure you have name selections. Free stream inlet. NASA does all of these regions. Boom, boom. So I do the same thing. Jet inlet. Here, nozzle wall. Here, these are going to be adiabatic. It says adiabatic, meaning no heat inflow or outflow. Outlet here. Axis of symmetry here. Make sure you update that. You create your solution, your setup. Solution, you want to make sure it's 2D. You could do it parallel, doesn't matter, parallel series. I run it traditionally parallel, depending on how much your computer can do. You want to, first thing, once this loads up, you want to make sure, so as a reminder, this is a subsonic but compressible flow because compressible flow is generally above 0.3 Mach number. So to make sure it's compressible, in general, you have to change pressure to density based. I would do steady state model. I would do Sublart Amaris one equation turbulent model because generally, even though the Reynolds number, if you like NASA notes that the Reynolds number is maybe 5,000, but realistically inside the nozzle, that air is moving so fast and it's injected by some fuel injection that it's bound to be turbulent. It's tripped flow. It's somehow it's very likely more turbulent. Uh, and you want to turn the energy equation on. Materials, you have to change your fluid, your air to be ideal gas, and the viscosity no longer constant, and it obeys the Sutherland law. Uh, you want it to be 3 coefficient, just leave this how it is. It's a good relationship between fluid flow and viscosity. For axis, you want to make sure this is still your axis of symmetry. You want to make sure on your general that it's 2D axis symmetry or axisymmetric, and this axis is considered an axis. Inlet, so this is kind of the interesting part that can create a lot of troubles if you have it wrong. So generally for compressible flow, you want your inlet and outlets to be pressure based. My free stream inlet, which is all around here, are pressure far fields. Pressure far fields act as if it's an inlet that's kind of an infinitely far away distance, and I keep that Mach number to be 0.01. Axial direction, meaning it's that way. Turbulent viscosity ratio, remember, is the ratio between the laminar viscosity to the turbulent viscosity, and that's what they use here. So I just copied it. Jet inlet, this is a pressure inlet. Interestingly, some people might be used to specifying velocity inlet, but in this case, you can even see that they don't specify a velocity inlet. They say this is what you expect, but you specify actually the pressure here. So they tell you your PT over P reference is 1.19671, and the P reference is atmospheric, which is what your operating condition is. So your operating condition is in your boundary conditions. Operating conditions 101,325 standard. So to get the pressure, I just take that 101,325 times that by this. So this is my total gauge pressure or total absolute pressure. I want to minus that by this. This is my gauge pressure, and this goes into your pressure inlet. And so that's what I have here. I have it axial component. Thermally, I have this all at 300 degrees Kelvin. They specify theirs as 530 Rankine, which is about 295. I just keep it all there. The wall, the nozzle, you want to make sure it still is a wall. So, yep, no slip, but also thermally, there's no heat flux. So it's important because it probably will mess up some of the heat characteristics if you have heat flux. I keep this also at the same temperature. Yep, don't need to touch any of this. Methods, implicit, no pseudo transient. Don't need to do any of this really. You can initialize it by hybrid, that's what I did. and you run it for, this took about, I believe, I've let this run about 4,000 iterations, and it looks pretty good for me. And it's a little bit unsteady at first, but eventually it reaches its steady state after a while. And so for me, how it looks is it looks like this. Boom, looks pretty good. It might not be converged fully, uh, but how I can compare it to this is they have a center line. They have U over U jet. U jet, I think, is just the average velocity across the U of the jet, and they're defining the jet as this, when it exits that. So that's that U value. So you can kind of see it like the jets. They're saying it starts right here. The jet starts right here. So if you block off everything before that, that's how it looks. So to get that line, I have to make a plot, an XY plot. What I first did is actually I probably created a line. I created a line, and to start here, I know that this starts at this 6.825 plus 0.25. So that's what, 7.4. Wait, sorry. I'm gonna break out my calculator really quickly on my phone. So that's 6.825 plus 0.25. So that's 7.075 x 7.075. And I want to make this go outwards to 80 x over r. R in this case is 1 inch, or whoops, 20. X equals over d. D is 2. So I want to, so that means this value of 20 is 40 over d, because d is 2, so x has to be 40 more inches than this. So I'm going to go about 47.075. So I create a line 15, and then I can create an XY plot. I will do this on line 15. Boom, on velocity. And here we go. This is how my velocity looks, like this. And so I can see that this is generally maybe between 6-ish. Well, let me look at the results. So it predicts about 6 to 7 it starts. And I can say, considering I have to shift it, so imagine it starts at 7. It's at about 21, maybe. So about 14. That's 14 inches over the non-dimensionalized 2. So it comes out to about 7. So if you want to export this, you write to file, you write this, and you save it as an XY file. And I actually have, to save time, let me open up my Excel. Oops, make sure. I already did this. And then you kind of have to nominalize some stuff. Unfortunately, I believe this is it. Is this it? Oh, this is actually the values of the nozzle. Whoops. I'm bound to have it. I swear I had it somewhere. I guess I didn't. Well, you guys are in luck. I will write this to file. Write. I'll call this ARN2 jet middle. Something like that. Whatever you want to call it. And then I will open. Whoops. Let me browse my computer. So yeah, unfortunately, it doesn't recognize it at first, but then you get, here, let me show you guys how it looks. So when you try to open it, looks like this. You have to go under all files. It doesn't trust it, doesn't recognize it, still open it. Then you kind of have to tab eliminate it. You have to delimitate it by a space. Finish it. And boom. So these are in meters. So I don't know why it exports it in meters, and this is meters per second. So what I'm gonna do is equal this. Now let me Google how many inches per meter. Okay, so I need to multiply this times this, and I can actually nominalize it. Minus, what did I start? 7.0, what was that number? 7.075. Yep, so it goes up to 40. And actually, I want to divide this by 2, right? So in this case, this divided by this 2, so I'm nominalizing it, make it non-dimensional like this, x over d. So my x, I converted this converts it to inches, this subtracts that initial 7, and then this divides it by 2. So, oops. All right, so this, and this is my meters per second. It's kind of weird what order. And here we go. That's how it looks. Now let's import the other file. So this is from, I believe this is another CFD code. The data from wind. Wind is down here. So I want the centerline file. I'm going to simply copy paste this. I need to delimitize this. And I believe this is, let's look at this file. So this is U over UJ. So UJ, they say, is, I believe, about 0.51. Yeah, if I remember correct. So Mach yeah, so this will be UJ. So assuming the UJ is the third column, I will multiply it, equals this times, don't know why it has to make me do this so long. And this is my x over dj. So I actually think I nominalized it too. So let's add data to compare it. Oops. And here we go. Boom. This is how it compares. So compared to NASA's other code, which again, this may or may not be perfect. NASA's one really might not be perfect either. But generally, they kind of go to the same region, 6 to 7, but my one expands a little bit slower, I believe. So it's kind of like that velocity drop off is not as early. But generally, if you're doing your own CFD study or some modification, I think this logic would hold up. Quick edit. Before I go into post-processing. Actually, I imported the NASA experimental data shown in the gray here. So the orange was the NASA CFD code. The blue is my own CFD simulation. And so I actually think my code actually follows NASA's experimental data a little bit better actually than their own code. I'm of course not using my own code. It's ANSYS Fluent. So it kind of shows that it still works pretty well. And I got it from uh, this result, this axisymmetric data set comes from a PIV of the exact same nozzle. So this is a comparison. This was the PIV data, and here it shows you your CFD data from NASA. So this kind of can compare the three different components to show that it is validated pretty well. And so now we can head into CFD-Post. One thing I can do too is show you how to post-process it to make it look whole. So you want to close out. You can open up results. This starts up CFD-Post. I don't know why it shows like this initially. Have zero clue really. Whoops, we just jumped to my previous solution. But this is how it can look if you mirror it. So I basically created three contours. Contour 1, I literally just, hey, I'll create a new contour. I, from my location, have to show periodic, which is this thing. I want to say 30 contours is good. I want to show velocity. Show me this. Boom. And that's how it looks. If I want to show it reflected because it's axisymmetric, all I have to do is say apply reflecting mirror. And then I want to flip it this way, so I want to know what this plane is, which is my ZX. Boom, so I flipped it. So now I just need to show two contours, right? So contour 1 is flipped, like exactly what I showed. And so let me just unflip this. And let me show contour 4. Boom. And now I have two contours showing, and this is the jet. So if I want to show only, if I don't want to show any of this, I would probably create a plane. On second thought, I probably would not create a plane. I just tried it, didn't work. If you want to take a picture, uh, why is this looking weird? It's because this number of contours is off. So make sure your contours are the same. You can increase your contour really. You can make it like 50, and it will really just add more color definition. Uh, it represents it more accurately. But yeah, if you really want to take a picture, just line it up with here. You could make a plane. I tried it a second ago, had some issues. What is cool is you can also plot the eddy viscosity. This is kind of like the viscous effects. Kind of cool in my opinion. But that's all I'm going to show for today. If you guys have any questions, feel free to ask me. So I showed you guys how to make the geometry. I started out with NASA's the nozzles themselves. A little Solidworks work, put in Solidworks, export it as a step file, import it into Design Modeler, kind of did the whole shebang. So hopefully this was helpful for some of you guys, and I'll see you guys next time.